These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. There's also, however, an important type of word problem here in section 5.4. So let's talk about that. Let's see. So let me give you this. Try this problem.
Okay. Velocity is first. So t squared. Okay.
Okay, excellent, good. I'll go back to my screen. So that was just some review. It's good that you remembered that. So the key there is you remembered V is S prime. Okay, excellent. What does S stand for?
S is the position.
Excellent. And what does V stand for?
V stands for velocity.
Right, good. All right, so that's good that we were reviewing those ideas. So let's think about an object that's moving, say, up and down. When the object is moving up, that means your velocity is positive.
Mm-hmm.
So what's going to happen when we're moving down?
Our velocity is going to be negative.
That's right. If we assume up is our positive direction. Now, what about when we shift from up to down, or shift from down to up? There's going to be one instant when we're changing direction.
Mm-hmm. That's the top.
Or the bottom, good. What could you say mathematically about the instant when you change direction?
Okay. So that is when V t equals 0.
Good. Can you see why? Because if you change from up to down, while you're moving up, V is positive. While you're moving down, V is negative. When you're shifting from positive to negative, you have to pass through 0. So V equals 0 at the instant when you change direction. It would also work if you bounced off the ground. So if you're moving down, your velocity is negative. Then when you start moving up, your velocity is positive. So when you shifted from down to up, your velocity must have passed through 0. Okay, so these are some important ideas. So how can you figure out when an object changed direction? If you know their velocity function, how can you figure out when they changed direction?
You can set it equal to 0 and solve for t.
Good.
So it sounds like we're kind of finding like the local max or min of the velocity function. Would that be true?
I'd say that was a nice try. That's good that you're thinking about that. That's great that you're thinking about that. That's great that you're trying to apply those ideas. Let's come back to that in a moment. That was a very good thing to think about. First of all, let's do this problem. Try this problem on your screen. Okay. Now, it doesn't really make sense to ask when v changed direction. The letter v is not moving. What we want to say is when did the object change direction? Because the object is the thing that's moving. We're going to use the object's v to figure that out, but it's not the function v that's changing direction, it's the object.
Okay. So would be good notation to do something like this first, v of c, or is that not needed?
You could write v. You could write v of c equals 0 or v of t critical equals 0. This is probably simple enough that we can just go straight to the equation that you have, though.
Okay.
That was a good thought too, but I guess we might as well keep this a little bit simpler. I think you understand the idea.
Okay, so yeah, so object changes direction at t equals 2.
Right. And if I'd given you units, you would put in the units. Your instructor cares about units, but I didn't tell you the units. Maybe it might be seconds. Okay, very good. All right, so I'll go back to my screen. Now, remember a couple minutes ago you were trying to kind of give a calculus interpretation of this, or a min-max interpretation. What was your min-max interpretation?
That t is 0 when, there is a local max or min when t equals 0. I think that's what I was saying.
Good. A min or max for who?
For velocity.
Okay, that was the part where we messed up. So remember, the velocity is s prime. When the derivative is 0, does that mean the derivative has a maximum?
No.
No. Who has the, when s prime is 0, who has the maximum?
S.
S. So that's why I said that was a good try, but not quite. You were on the right track. So v doesn't have a maximum. V is 0 at this point. V is 0 at this point, not a maximum or a minimum. But the position function has a maximum or a minimum. The position function has a maximum or a minimum at t equals 2. Does that make sense?
Yep.
That actually is just common sense, right? Because if you're changing direction, that looks like this, right?
Mm-hmm.
So notice the point where you changed direction, position was at its maximum. Or if you bounced off the ground, the point where you changed direction, position was at position was actually at its minimum. So this is actually almost kind of a proof of that law of calculus that we were talking about before. So it's not the velocity that has a minimum or a maximum at t equals 2. It's s that has a minimum or a maximum, because when s prime is 0, s has a minimum or a maximum. At least those are the candidates. Okay? So that's good that you were thinking about that. It's going to be important for us to graph v for these word problems. So I'll make a graph here. What goes on the horizontal axis?
Time.
And what goes on the vertical axis? Well, I just said we were going to graph v, not s. So I'm going to put v on the axis here. This is a little bit weird because that means we're graphing s prime. Usually we graph the function, but here we're graphing the derivative.
Mm-hmm. Okay, so
where do we cross the t-axis? Where does v cross the t-axis?
v crosses the t-axis at
So
at 2.
Yeah, how do you know? When you're on the t-axis, what's your v? When you're on the t-axis, what's the v for these points?
0.
0. So that's what we found. We found that v is 0 at 2.
Mm-hmm.
All right, notice, would you agree this looks like the equation of a line?
Yeah.
And what's the slope of this line?
4.
Yeah, mx plus b. So should the line be upward or downward sloping?
Upward sloping.
So notice we can get the basic shape here just from knowing where it crosses the axis. We know that the graph basically looks like this. If we know where it crosses the t-axis from this information, then we can, and we know whether it's upward or downward sloping, we can draw our graph. Let's check that on our calculator. We'll have to use x instead of t. So what's the function that we're going to plug in here? Well, we're graphing the v function. So negative 8 plus 4x. You changed your window, so you should go back to Zoom Standard. Tell me when you've got a graph.
This thing's really slow. Zoom Standard. Okay.
Does your graph look like this?
Yep.
Okay. And notice we kind of figured it out on our own. So the calculator here is just for confirmation. We've basically figured out the graph from our own work. But you can't only use the calculator because your instructor is going to want to see that you solved for where v is 0. So we need to be able to do that part without using the calculator. So between time 0 and time 2, and I wouldn't probably want to do this. You don't do this because probably the experiment started at t0. So on your calculator, the line goes on forever to the left. But on your graph, it should start right here, starting at t equals 0. So in this region, is v positive or negative?
Negative.
What does it mean when v is negative? What does that tell us about how the object is moving?
When v is negative, the object is it's moving downwards.
Moving downwards, yes.
Yeah.
And is v positive or negative here?
Positive.
Good. What does that tell us about the object's movement here?
The object's moving upwards.
So here's a little movie of the object. T equals 0, t equals 1, t equals 2, t equals 3, t equals 4. That's what the object's movement must look like. It fell down, then it moved up. So again, fell down, moved up. That's what we can figure out here. So notice we used the derivative to figure out the motion of the object. This shows how calculus is useful. This problem never told you the position, but just from the derivative from s prime, we were able to figure out how the object was moving. First down, first up. We know it changed direction at t equals 2. That's where it bounced off the ground. Okay, so that's a skill that we're going to need for this section. One moment. So we need the concept of displacement. Displacement is S final minus S initial. So let's say we start here, and then we move here. And then we move here. Tell me when you have all this written down so far.
6, 4. Yep.
Okay, so now we're going to figure out the displacement.
Okay. So we started at 0 and we ended at 4. So the object only really moved 4 units.
Okay, so what's position final?
Position final would be 4.
And position initial?
0.
Good. You know, actually, maybe I shouldn't write it that way. What do you think TF stands for?
Time final.
Right, and ti.
Time initial.
Now, this is a little weird here because I didn't tell you the times. But you don't actually need to know the times to know what the final and initial, what the position was at t final. So we're not plugging in for t here, but we're plugging in for s. So what was the answer?
4 units.
Good. +4 or -4?
Let's see. We started at 0 and.
Now, actually, what I wanted. Oh yeah, I'm sorry. Go ahead.
I would say +4.
Good. I think you saw it because we ended up above where we started.
Mm-hmm.
But we should also confirm that with the math. What answer did the math give us, positive or negative?
A positive number.
So that confirms that that's correct, although you could just see that as well. So in order to get this sign to come out right, it's always got to be s of t final minus s of t initial. You always have to subtract the final first, then the initial. Always final minus initial. Never initial minus final. That's pretty important. So notice it's not big minus small. You don't subtract the big number minus the small number. You subtract first final minus initial. Okay, so that's how we would calculate displacement in that case. So let me give you another example. So first we went from here to here, then we went from here to here.
Mm-hmm.
So calculate the displacement.
Okay, so we started at 2, and then we ended at 1. So we would have our final was 1, so 1 minus our initial, which was 2. 1 minus 2 is -1.
Why did it come out negative?
Because we ended lower than where we started.
You could have predicted it would have been negative, but the math confirmed that. So I noticed you paused there when it sounded like you were considering what order to subtract these, but you got it correct, like so. Of course, if there were units, you'd have to put in the units here as well.
Mm-hmm.
Okay, so notice, what would be the mistake? Notice this is not 2 minus 1. It's not big number minus small number. It's final number minus initial number. Okay, very good. All right, so that's the concept of displacement. Now we have another concept which we have to go over, which is the concept of distance. Distance is what your odometer would read. So imagine that there's a little odometer on the object. Do you know what an odometer is?
The thing that tells us miles per hour?
That's the speedometer.
Okay.
So you know what, in your car, there's something that tells you how many miles you've driven since the car was bought?
Yep.
That's the odometer. Okay. So yeah, so we're not thinking about the speedometer, we're thinking about the odometer. So notice, would you agree with me? Well, actually, let me give you this example. One more example. What's the displacement here? The displacement.
0.
Good. You can just see that from the picture. We ended up at the same place we started, but how would you calculate that mathematically?
Our final value was 2, because we ended at 2, and then our starting value was 2. So 2 minus 2 is 0. Our initial value, I should say. Yeah, 2 minus 2 is 0.
Okay, excellent. Now, but would you agree then, an odometer, if you drove from here to here, now we're thinking that this is now not up and down, but maybe north and south. Maybe this stands for north and south. If you drew to here and drew to here, your odometer wouldn't read 0, would it?
Right.
So would you agree your odometer does not measure displacement?
Right.
Yeah, the odometer doesn't measure displacement. Displacement's a wonderful concept, but that's not what the odometer measures. Although that might be a good nice stuff. Maybe you can make a fraud technique or a joke about that some unscrupulous used car salesman who changes the odometer to lower the number of miles, and when the judge is ready to put him in jail, he says, "Well, this is just a displacement odometer, not a distance odometer." I don't know, seemed funny to me. All right, so in any case, so what do odometers measure? Odometers measure distance. So the distance is just what, it's a little hard to put into words, but the distance is what your odometer would measure. It just counts up all of the actual miles you've actually traveled, all as positive numbers. So notice, is it possible for displacement to be negative? Is it possible for displacement to be negative?
It is.
We got a negative answer before, right?
Yeah.
But distance is always positive. You might have noticed that you never see any negative numbers on your odometer in your car. Distance is always positive. I don't know if that made sense, but so what's the distance? What's the distance that this object traveled?
4 units.
That's right. How would you do that really mathematically? Well, that should just be obvious, but if you were going to be nerdy about it and do it mathematically, distance has to be calculated in separate parts. You figure out the distance you traveled in one direction, then you figure out the distance you traveled in the other direction. So we could call this T0, T1, and T2, because T1 is where we change direction. And then it would have to be S of T1 minus S of T0.
Plus.
And now you figure out the distance you traveled on the other leg. S of T2 minus S of T1. That tells you the distance you traveled on the two legs. And we need absolute values because distances have to be positive. So what's S of T1 here?
4.
And S of T0?
2.
And S of T2?
2.
And S of T1?
4.
4 minus 2 is 2. What's 2 minus 4?
-2.
What's the absolute value of 2?
2.
And what's the absolute value of -2?
2.
So what's the distance?
4 units.
Now, in this case, it was obvious it was 4 anyway. You could have just counted it out. But for our word problems, we're going to need this long way. For the word problems, we're going to have to calculate the distance. So by the way, do you see now why we had to practice learning how to figure out where the object changed direction? Now you can see why that's important. You need to know where the object changed direction in order to calculate distance. Right? We need to know where the object changed direction in order to calculate the distance. Because you have to do, while it's moving in one direction, you have to treat that separately from when it's moving in the other direction. Otherwise, you'll accidentally miscount the distance. You'll treat it like a displacement. By the way, notice you don't really need to worry about what order you do these subtractions. Because if you had done this as 4 minus 2, you would just have gotten +2, but it doesn't make any difference because the absolute value of -2 is the same as the absolute value of +2.
Right.
So the order of these subtractions doesn't make much difference. The order of this subtraction is crucial for displacement, but not here. But maybe it's better to write it this way for full credit so that the reader knows that you're thinking about that right. Okay, so that's our concept of distance. Let me write this down then. Of course, you could also apply these techniques to objects that are moving left and right, or east and west, but I think it's clearer to think about it here if they're moving up and down or north-south. Okay, so here's another object. It moves like this, up to here, then down to here. In reality, it's moving along the same line. I'm only putting these separate because otherwise they'd overlap with each other. Okay, well, talk me through how you would attack this. You can try this on paper and tell me what you're writing down.
So for displacement, the object started at 4.
And let me interrupt for a second. So what? I'm sorry, but what's this axis measure? How should we label this axis?
That axis measures S.
Not good, not V.
Right.
Otherwise, because I said this is how it's actually moving. If this is how it's actually moving, this must be its position. So notice this is different. Earlier, we did a graph where V was on the axis. earlier we did a graph where v was on the axis, but now we've shifted to a picture where s is on the axis. So we just have to be careful to always ask what the axes are. Okay, sorry, so go ahead and try, tell me how you would work that out.
Okay, so we started at 4 and we ended at 1, so we have a negative displacement, and that value is -3. So 1 minus 4 is -3.
Excellent.
Okay, and for distance, well, we definitely traveled 10 units, but to show the math, we have to do, let's see, the absolute value of 7 minus 4 plus the absolute value of 1 minus 7.
Good. Final minus initial is the best way to write
Right.
it. Final minus initial. Good.
And that will be 3 plus 6, and that is 9. So why did I say 10? Oh, because it's 7 and 3. So why did I say 10? 4, 5, 6, 7. 4, 5, 6, 7.
What's the distance from 0 to 7?
7.
Good. But what's the distance from 1 to 7?
6.
So that's where you were going wrong. You could also just count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So basically what happened here is this is where it was a good idea to actually work out the math. What you actually did is you did it in your head as if this was 0 minus 7. You did it in your head as if it was 0 minus 7 when it's really 1 minus 7. Okay, that's excellent. That's perfect. Now, in order for us, these are not what the actual problems are. These are just prep work for the problems. The prep work here is we need to see how to write this algebraically. So what's the algebraic formula I would write up here?
For displacement, we would write, let's see, TF minus TI.
Not quite, because these numbers are not times.
Okay, yeah. SF.
What goes in here?
F. Well, I think we changed it to TF.
Yeah.
Minus S of TI.
Okay, good. This is actually what the most important part here. This is what we're going to need for the actual problems. We need this expression. So this is the expression for displacement. That's more important than these numbers here. This is important. So you should study this after today to see, make sure you're getting this expression. This is what we'll actually need for the word problems, not the numbers. Then how about the distance? That's a little bit more complicated. What's the mathematical expression for that?
Okay. The absolute value of, let's see, T2 minus T1.
Now we're not subtracting the times. These are not times.
Okay. S2 minus S1 plus.
What goes in here?
T2.
So not 2, but T2. And what goes here?
And T1.
Good. So what we might do now here is go back. Let's actually call this T0. Well,
Okay.
no, all right. You could call it T0. That's not important. We'll call it T1. Then what's this?
T2.
And what's this?
T4.
Well, you could call it that, but why not call it T3? Because this is the next time we care about. All right. So then what goes here?
T1 plus the absolute value of T3. The absolute value of S of T3 minus S of T2, I guess, because it's the same as, okay.
And what was S of T2 on this problem?
7.
Yeah, you can see that matches up. Remember, what's this axis measure? What's the variable on this axis?
It's the position,
S.
S.
So notice how you had a tendency here to say T2 minus T1, but this is not a T axis, it's an S axis. S axis. Okay, now again, this is what we actually need for the problems.
Okay.
This was just kind of practice and understanding. So this is the part to meditate on here. We'll need this going forward when we change this into calculus. You need to understand how to come up with these expressions here. So that's what you should really study here. That was what was giving us trouble too.
So there's never going to be like there's never going to be a problem or like some type of problem where the T2 for the right hand side when I'm not trying to word this are we ever going to have like a T4? I mean, because I wanted to label the top T3 and then the bottom T4.
You mean like this?
Yeah.
Yeah, that's an optical illusion. Remember, these 2 points are the same exact point. Mm-hmm. Remember, the way the object is actually moving is like this. Here's a movie. It's going up, going up, going up, going up, going up, going up, going down, 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 down. That's the end. So the point is, it's all traveling along the same line. The only reason I didn't draw it that way is because then the upward portion would be covered up by the downward portion. Mm-hmm. So this point in time must be the same exact point in time as this.
Right.
So it doesn't make any sense to use different symbols for them. These have to be the same symbol. You were asking if there would ever be a T4. Well, there would be a T4 if then it moved up again.
Okay. No, it makes sense. I was just wondering.
So if we moved up again, then there would be a T4. Let's think about this a little bit more. What's the meaning of T2? What does T2 stand for?
T2 is it's the absolute max of S.
That's right. But what's another way to put it? It's the point where we change direction. Mm-hmm. Remember, that's what we were talking about earlier? That's what we were calculating up here. When is the object going to change direction? So this is the point in time when it changed direction. Well, there's only one point where it changes direction here. That's why this number is the same as this number. The T2 is the same on both sides. There's only one point where it changes direction. How would you know what T2 was? How would you know when it's changing direction? Well, we learned how to do that earlier.
Yep.
You're going to be given the velocity function. So do you see how we would put these pieces together? What they're going to do is, so this was just warm-up. On the real test, they're not going to give you the position. They're not going to give you the position on the test. They're going to give you the velocity. Okay. And then one thing you're going to have to do is figure out where did the object change direction. Well, we know that we do that by setting the velocity equal to 0. And then we'll be able to set up these expressions. So we're not. There's still some more we have to see how to do, but those are some of the steps that we're going to need here. Obviously, we'll have to now go on next to see how to use calculus for this. But this gives us the basic ideas. So that's about our time for today. So the thing that would be most helpful is, again, studying how we came up with this line and this line. These are the key that we're going to have to build on. Going forward here with those 2 lines. Let's see, anything else?
Yeah, I'll definitely go over today's session. That's what I usually do. I usually just I try and make sure to rewatch the whole video or most of it anyways. So.
Great. So now that we've done this, what would be a better name for these 2 times? Which time is this?
Displacement.
Now that we've relabeled this graph.
Okay. That would be T3 minus T1.
So actually, I think the best way to do these is first label the points in time. Then do these expressions. Mm-hmm. First we label the points in time, and then we do these 2 expressions, and then we can see what to put in for this. Okay, so that's the first steps for doing that type of word problem. I'm pretty sure there's going to be one of those word problems on the sample test, so we'll be able to finish that up. What does this symbol stand for?
That is position.
And what's this symbol stand for?
It's velocity.
Good. What does this mean?
Velocity is negative.
What does that mean?
That means that the object is moving downwards.
That's right. And what does this mean?
That the object is moving upwards.
Good. How do you know when it's changing direction?
When velocity equals 0.
Great. Now, how would you describe in words what's the relationship between s and v?
V is the first derivative of s, and s is the antiderivative of v.
This is something we learned a couple chapters ago. This is something we learned a couple of chapters ago because v is the rate of change of the position. And now that we've learned the new term antiderivative, we know that if this is true, this must be true. Maybe you should say this is an antiderivative because there's many of them. But otherwise, that's a correct statement. Okay, so now let's say this is not a calculus question. Can you figure out what would be this object's displacement?
V equal 3 feet per second for 4 seconds. Its displacement would be, well, in this case, it would be the same as distance. It would be 12 feet.
Great. So that's just a high school word problem. If you go 3 feet per second for 4 seconds, it should be obvious that your displacement is 12 seconds. And you're right, in this case, the displacement is the same as the distance. When is the displacement the same as the distance? They're the same when you don't change direction, right? If you're only moving in one direction, there's no difference between displacement and distance. There's only a distinction when you change direction at some point. So you can call this the displacement or the distance. All right, so this isn't calculus, this is just common sense. If you travel at 60 miles per hour for 2 hours, how far did you get? If you travel at 60 miles per hour for 2 hours, how far did you get?
You traveled 120 miles.
Yeah, just common sense. Okay, good. Now, how would we graph that? How would we graph this function, v? Well, would you agree that in this case, v would be a horizontal line?
Mm-hmm.
Because it's constant. Why is everything slanting here? All right, I didn't mean for everything to be slanting here. All right, this is supposed to be a rectangle.
Mm-hmm.
So do you agree this is the same situation here? They traveled at, this is the same situation. They traveled at 3 feet per second for 4 seconds between 1 and 5. So how far did they travel?
12 feet.
Good. 12 feet. What's the area of this rectangle?
3 times 5, so 15 feet.
Now careful. What's the width of the rectangle?
4, so it's 12 feet.
Yeah. So what's the area here?
12 feet squared.
Let's see. Well, what are the two numbers that you multiplied times each other? Okay. Now, what did you multiply? You multiplied. Yeah. What were the two things you multiplied?
4 and
4.
3.
What were the units on the 4?
No units.
Well, it's 5 seconds minus 1 second. So the units are
4 seconds.
And what are the units on the height?
Feet per second.
So what units do you end up with?
Just feet.
Just feet, not feet squared. You might have said feet squared because areas are usually measured that way. But I'm not actually saying that this patch of white on my screen is 12 feet. We're saying that it represents an area of 12 feet. Anyway, something should jump out at you here. The area under the curve is the distance.
Mm-hmm.
These two numbers are the same. Amazing. So all this time we've been talking about areas under curves, right? We've been talking about areas under curves, but we didn't say, why do we care about areas under curve? What do they mean? Well, here's something very interesting. What we see here now is, what is the area under the velocity curve? It looks like the area under the velocity curve is the displacement. We just kind of proved that in this case. The area is 12 feet, and the displacement is 12 feet. So based on that little argument, we can say the area under the velocity curve is the displacement.
But it can't be the distance, right?
Well, in this case, it would be both the displacement and the distance. In general, it'll be the displacement. In general, it'll be the displacement if you treat areas below the axis as negative. If we treat area, actually it depends. If you treat all the areas as positive, then it's the distance. If you treat areas below the axis as negative, then it's the displacement. All right, well, we won't get into that in too much detail right now. All right, so anyway, we discovered what the area means here. Area under the velocity curve is the displacement. Now, we've only proven that when the velocity is horizontal. We've only proven that when the velocity is horizontal. You'll just have to kind of take it on faith for the time being. That is also true if the velocity was a curve. Even if the velocity was a curve, the area under the velocity graph would still be the displacement. We're not proving that, but that should seem reasonable because it's true when the velocity is horizontal. Clearly, when the velocity is horizontal, the area under the velocity curve is the displacement, and that should make it easier to accept that even when it's not horizontal, the area under the velocity curve is still the displacement. Okay, so we'll write that down. Remember last time the displacement was given by this formula?
Mm-hmm.
So that means the area under the velocity curve is given by this formula. Now remember the velocity curve, would you agree that this velocity curve is S prime?
Yep.
So we could also say the area under the S prime curve is this. Okay. We've proven that when the velocity is horizontal, and it's still true when the velocity is not horizontal. Let's see. Now, one concept we've talked about together is the definite integral.
Mm-hmm.
What is the graphical interpretation of the definite integral? What's the graphical interpretation of a definite integral?
Okay. The definite integral shows you the area between the x-axis, or it shows you the area between the axis and the curve.
Excellent. Well, here I have written down area under the curve. Well, areas under curves are definite integrals, so we could just as well call this the definite integral of the S prime function. That's the same as the definite integral of the V function. Because remember, S prime is V.
Mm-hmm.
Well, that must then be equal to this. That's equal to this expression here. Well, remember, S is the antiderivative of V. S is the antiderivative of S prime, so what we've got here is that the definite integral is the antiderivative at the right endpoint minus the antiderivative at the left endpoint. I'm just rewriting the previous equation. The area under the curve is the definite integral. And this minus this is the antiderivative at the right endpoint minus the antiderivative at the left endpoint. So what we just did here is we just kind of proved the fundamental theorem of calculus, part 2. This is the fundamental theorem of calculus, part 2. We just proved that that's true when the curve is horizontal. We just proved or explained why that's true when the curve is horizontal, and then we kind of have to take it on faith that it would still work even if the curve was not horizontal. But at least this should if you meditate on this, you can kind of see why this fact that we've just been kind of taking on faith kind of makes a little bit of sense. If we look at the velocity and distance example, and think about when the velocity is horizontal, we can kind of start to see why the definite integral can be discovered by using these antiderivatives at the right and the left endpoint. We can see why the area under the curve can be found by taking those antiderivatives. Okay, so one advantage of this is now we've kind of proven or suggested why the fundamental theorem of calculus is true by looking at the case where the curve is horizontal. How can we use this to solve the word problems here? Well, we can sum this down to displacement. So the displacement equals, we've just discovered here the displacement is the definite integral. It's the area under the curve. So this is the equation now that we'll use for solving the word problems. This little example here proved that when the curve is horizontal, the displacement is the definite integral. And it turns out that that still works even when the curve is not horizontal. The displacement is the definite integral. So this is the formula we can use for solving problems. And then we can adapt that to problems about distance. Let's see. Does this make any sense so far, how we got this equation?
Yeah, it does.
Okay. Now, how would we find distance? Distance is going to be a little more complicated. There's a two-step process. First of all, step one, we have to find where the object changes direction. Let's call that T1. And then you can use this formula. Okay, so here's the formula for calculating distance.
Okay.
Tell me when you have that written down.
Yep.
Okay, so now we've kind of proven that this was true when the curve is horizontal. Remember we saw that when the curve is horizontal, the distance and the displacement are the area under the curve. And it turns out that that still works even when the curve is not horizontal, even though we haven't proven that. Notice how these formulas are very similar to here. The only difference is it possible for displacement to be negative?
It is.
So for displacement, we want a definite integral, which is positive when the curve is above the axis and negative when the curve is below the axis. But we talked last time, is it possible for distance to be negative?
It's not.
No, remember your odometer never goes into the negative. So here's what we have to do to make sure the distance always comes out positive. We have to split this up into two parts. One when the object is moving in one direction, and the other when the object is moving in the other direction. We did some examples like this yesterday, and we just take the absolute value of each of those displacements. So we're using the same formula as here, but we're taking the absolute value to make sure that they come out positive when we add them together. We did problems like this yesterday where we saw that the way to find the distance was to break it up into two parts. Now, of course, this assumes the object only changes direction once. This assumes the object only changes direction once. If the object changed direction another time, then there would be a third term for that other part of the journey. And if it changed direction another time, then there would be a fourth term for that other part of the journey. And if the object never changed direction, you'd only need one term. But in the homework and on the sample tests, there's always two terms. So that's how I wrote it down. In the homework and the sample test, there's always a one change of direction. So hopefully we'll practice that, and hopefully that's what the test will be like.
Okay.
Okay, let's see. Okay. And we kind of proved that these two equations make sense when the velocity is horizontal, and it turns out that they still work even if the velocity is not horizontal. So let's look at a sample problem and see how this would be tested.
You mind if I give this one a shot, or do you want to work through it together? Either way.
Let's see. Okay, go for it.
Okay.
So, okay, so you can try it on your screen.
Yep. Okay, so displacement. So we're at 1 and 4 of vt with respect to t. So we need to find antiderivative of vt. Oh, this is a template. Okay. Okay, so the antiderivative is 2, 3 halves t squared minus 9t 1 to 4. Okay, so again 4. Divided by 2 times 4 squared plus 9 times 4. 4 squared minus 4 close bracket minus bracket 3 divided by 2 times 1 squared minus so 9 close bracket. And this is what I get, and I guess I can I'm not sure if my calculator can do this, but I could try graph this function and then use my second calc. So 3x minus 9, and then second calc 7, lower limit 1, upper limit 4. Yep, it gives me negative 4.5, so that's good. And this is in feet. Okay, and then B. So B, we're trying to find distance. And so from 1 to 4, the velocity of an object is given by some function on some time interval. Find the displacement and find the distance traveled by the particle during the time interval. So if it displaced negative 4.5 feet.
Oh yeah, this one we should work on together a bit.
Okay.
The key here is, if you remember the two-step process that I had written on my screen, in order to find the distance, you have to find where the object's motion changed direction.
Okay.
The first step is to figure out where we change direction. Because you can only figure out distance on an interval where it's moving in only one direction.
Okay, so we found where it changes direction, and then we have to, and that's t1. So we'll say t1 equals 3.
Because we call the first point in time t0.
So we can write our distance equation like this. So t0 is well, I know 3 goes up here. t0 is just at time 0 of the velocity function. So 3t minus 9 respect to t. And then 3, and then the final time. Or the final time. So if we started at 0 and we got to 3, it displaced, so the final time was negative 1.5.
Sounds like we're getting confused. I'm not sure how time can be negative. What was the question asking us for?
The distance traveled by the particle during the time interval.
Which time interval?
1 to 4.
That's right. I think you forgot that time interval.
Okay. So we started at 1. But we don't use t1 equals 3. Then we also used 3 to, okay.
If we stop and think about it for a while, hopefully these equations will make sense and we won't just be kind of using them mechanically. They're very similar to the equation up on top. Up on top, we found the integral from 1 to 4, because that's the time interval. But remember that when you're doing distance, you have to figure out the distance traveled while you're moving in one direction, and then separately the distance while you're traveling in another direction. You can't do them in one swoop. Do you see why it wouldn't make sense to say the time was negative 1.5? Yeah, because time is generally going to be a positive number on this type of problem. Okay, so we're still using the same time interval from 1 to 3 that we did before. What's special about time 3?
Time 3 is where the object changes direction.
That's why that's the boundary between those two. Okay, so now we have the correct formula.
Okay, so, okay. Yeah, just one question. So if it starts at 1 and it ends at 4, 4 and 1 are most likely at the same point, but not necessarily.
Let's see, I'm not quite sure if I followed that. What do you mean by saying they're at the same point?
So if I'm standing at the 50-yard line at time 1,
right,
and I throw a ball up in the air, and then it comes back down, time 4 is when it comes back down, but it could still be at the same point. Right?
Now, so the key thing here is we're not saying that the object stopped moving at time 4. We're saying we're going to stop the problem at time 4. We want to know what its distance and displacement were between 1 second and 4 seconds. It might have been moving before 1 second, and it might have been moving after 4 seconds. Also, you shouldn't be too committed to the idea that we're throwing a ball up in the air. We might have used that example before, but for all we know, this could be a rocket that's moving up and down in the air. It could be a hummingbird. that might be actually a better example. A hummingbird that's moving up and down. There's no reason that a hummingbird has to stop at the same place that it started, right? So I guess you're kind of assuming that the object has to get back to where it started between 1 and 4, but there's really no assumption for that. In fact, we know that's not true, right? Because what was the displacement between 1 and 4?
It was this value right here.
What does that mean that it's negative? Did the object end up above or below where it started?
It ended below.
Yeah. All right. So we can't assume that the position at the beginning point is going to be the same as the position at the end.
Okay. So now I take the antiderivative. So
Okay. Now the absolute values ended up in the wrong place. The absolute values are being taken of the definite integrals. Notice in your first notation, first you're going to take the definite integral, then you're going to take the absolute value to make sure it comes out positive.
okay. Okay, so So bracket 3 divided by 2 times 3 squared bracket minus bracket 3 divided by 2 times 1 squared minus 9 bracket. I'm going to split these ones up. 21 plus, well, the absolute value of 21 plus bracket 3 divided by 2 times 4 squared times 4 squared minus 9 times 4 is bracket minus bracket 3 divided by 2 times 3 squared minus 9 times 3 bracket.
All right, I think we need to check those calculations. Talk me through again the first calculation for how you got the 21.
My calculator's a mess. I don't know how to get back to it now.
Did you try using the second enter?
Yeah, I did.
Okay. All right. Try just going down to the, just enter a couple keys and hit enter, and that should put you down at the bottom of the stack again, and then you can try going up again to find it. If you can't find it, we can just go through it again.
Okay, so for the first part, I typed in bracket 3 divided by 2 times 3 raised to 2 minus bracket 3 divided by 2 times 1.
Oh, okay. Well, check what you have there against what you have written on the screen. I don't think they're the same.
3 divided by bracket 3 divided by 2 times 3 squared. Yeah. Okay. That's a big problem. Okay.
Yeah, it's very easy to make mistakes in the calculators. The key thing is just to slow way down and double check each step. So let's try that again. One thing, okay, yeah.
Three divided by 2 times 3 squared minus 9 times 3 bracket 3 divided by 2 times 1 squared minus 9 bracket. Totally different number.
Good. I think in the long term, you'll probably make fewer calculator mistakes if you simplify a little bit more. What's 1 squared?
Just 1.
And what's 3 halves times 1?
3 halves.
And what's 9 times 1?
9.
So I think in the future, you don't have to do that right now, but in the future, if you make those simple simplifications, it'll make it a little easier to type it into the calculator.
Okay. And then double check. 3 divided by 2 times 4 squared minus 9 times 4 bracket minus bracket 3 divided by 2 times 3 squared minus 9 times 3 bracket. I get the same number, so the answer should be negative 4.5. Well, no, that's not right. 6, so 7.5.
You can find the absolute value in your head. Good. Okay. All right, that gave us a little trouble. I think that came out right now. So what's the answer for the distance?
7.5 feet.
Yeah, very important to put in those units. Your instructor's definitely looking for that. All right. Well, I'm pretty sure you'll see a problem like this on the test. So one thing I think your instructor is going to want on this is to draw a graph of the velocity function. So let's draw a graph and label the axes so that we can, what would be the correct axes if we want to graph the velocity function? I think we can fit that into our top right corner.
Okay.
Remember, yeah, okay, good. We don't really need a very big negative x-axis here, but we are going to need a negative y-axis. Now, where does, yeah, okay, good. Let's label the two axes.
Okay, so time and then or graph velocity, so v.
That's right. Now, where will the velocity curve cross the t-axis? Where will the velocity curve cross the t-axis?
At 3.
So let's put that in. Let's put a dot there. Now, what's the equation of the velocity graph?
3t minus 9.
So what's its slope?
Positive upward slope.
So you can draw that. Good. And in fact, I think you already looked at you can check that on your calculator, right? I think you've already graphed this equation on your calculator, and you saw the graph look kind of like that. In fact, if you go back to the graph, where does the graph show the curve crossing the t-axis?
At 3.
At the third hash mark. So that's a confirmation that we got that right, although we still have to do the algebra to show that. Good. And in fact, then maybe your instructor wants a little bit more. So what's the starting time?
Starting time is, I guess 1.
Yeah,
1.
So pull the curve back to t equals 1 and show the triangle. That gives us, and then what's the ending time?
At 4.
All right, and you might shade in those two. Those are the two areas we're trying to find. So when you did the displacement, how could we see from the start the displacement's going to come out negative?
Because this area that's under the t-axis is a bit bigger than the area that's above.
That's right. In fact, how big is the area under the t-axis? What was the area under the t-axis?
2.
Well, actually, you already figured that out. What did you already figure out was the area under the t-axis?
The area under the t-axis is...
Where did we figure that out in all the work that we've done so far? So that's the area between what two times?
Between 1 and 3.
So where in your work did you figure out the area between 1 and 3?
Right here.
And you got
negative 6.
6. Right, that's right. All right, so we already know that area is 6. And what's the area above the axis?
1.5.
That's right. So you can see the area below really did turn out to be bigger than the area above. So how did the distance come out to be positive? Even so, because we took the absolute values there. Okay, so I think on the test, your instructor wants you to draw that graph too. That's what everyone was what people were doing on the sample tests. I think that's what he does in his answers. So notice you can find where it crosses the t-axis by algebra, but then you can confirm that's right on your calculator. As well. All right, so to review, this is important. So the displacement was relatively straightforward. We just took the integral over the entire time. The distance gave us some trouble. What was the very first thing we had to do to figure out the distance?
So if you're trying to find distance, the first step is to find when the object changes its direction.
That's right.
Yeah.
Which way was the object moving before time 3? Before time 3, was the velocity positive or negative?
Before time 3, the velocity was negative.
That's right. So which way was it moving originally?
It was moving downwards.
And then after time 3, it was moving
upwards.
But it didn't quite get back to where it started because we didn't give it enough time to do that. All right, so the first step is figure out where the velocity is 0, and then you can write down your distance formula. Remember, we also had some trouble knowing what the limits of integration would be for the distances there. But hopefully now we understand that, so it makes some sense to us that we want to start from the starting time up to the point where we change direction. And then the second integral is from the point where it changed direction to the ending time. Hopefully you could figure out what to do if it changed direction a second time or a third time. That would just be another term, but hopefully he's not going to make it quite that complicated on the test. We might stick with this. Okay, is that problem making sense?
Yeah, just a question. Yeah. So it seems like if there was a problem where, like, if the ball bounced multiple times, I know it's just the ball example again, but if so, wouldn't you have a new function to solve for when when the velocity equals 0? It would be different, wouldn't it?
Well, I guess what you're saying is that if this was a ball that was bouncing up and down, you're saying that the function would be more complicated.
Right.
And that's true. So this can't actually represent a ball that's bouncing up and down. It's more like it's more like a hummingbird. It's like a hummingbird. You should think of this. This is a hummingbird that starts up in the air. It flies down to a flower, and then it flies back up away from the flower. So notice it has to slow down as it's getting closer to the flower so that it won't crash into the flower. But then when it flies away from the flower, it starts flying faster and faster and faster. You can see the velocity is increasing. So that's not how a ball would work. A bouncing ball would get slower and slower and slower the higher it got. So this is not like a bouncing ball. This is like maybe, say, a hummingbird that's flying down to a flower and then flying up away from it. That's probably that. So that's a good thing to think about. That's more thought than we need for this problem. But so the key thing here is don't assume this is just a ball that's in free fall, a bouncing ball. It could be something that's moving around under its own power. It is true. So it is true that a more complicated movement might need a more complicated function. But fortunately, your instructor is probably only going to give you pretty simple functions like this. It's also true that it's possible that eventually the function might change. And then you'd have to change to a different velocity function, but hopefully your instructor is not going to give you a problem that hard. So basically what you're saying is the way real objects move in real life would oftentimes be more complicated than this, and that's true. But fortunately, we have to start with the simplest cases, and that's what this is like. And fortunately, I think that's what your instructor is going to stick to for the test, if that makes sense.
Yep, absolutely. And just one question. So on the time that I'm drawing this graph, do I need to draw the y value, or the v value as well? Like I guess you can see that 6 here.
Let's see. How did you know it was 6 there? Let's see. So first of all, you definitely don't want to show it unless you're sure it's right, because that gives you the grader an excuse to take off points. That should be a -6.
Okay.
Right. Okay. There's no need to put that in. You didn't need that for the solution. Now, that it is kind of interesting because that lets you confirm that the definite integral worked, right? Because that's now a triangle. What's the height of that triangle?
The height is 6.
And what's the base?
The base is 2.
So the area would be 1/2 2 times 6.
Mm-hmm.
And what is 1/2 2 times 6?
The absolute value of -6.
So it would be 6. So that just confirms that the definite integral really did figure out that area. And remember, we found the definite integral using antiderivatives. So that proves that antiderivatives really do give you areas. But that's not really, that's an interesting thing to look at, but I don't think that's necessary for the test. No, for the test, you should just label the t values.
Okay.
Okay. All right. So this is important to study here to see how we did this. The key things are, for distance, you have to know when the object changes direction and then split it up into 2 parts. And notice how the absolute value signs stayed on the outside of the definite integrals to make sure that we ended up adding 2 positive numbers. Let's go back to my screen. How would you check your distance answer on your calculator? Or maybe you need your notes for your screen. So remember that your distance, what was the first integral that you found to find the distance? You found the integral between where and where?
1 and 3.
So let's check that on your calculator. What do you get?
Let's see. 1 and 3. I get -6.
Let me catch up with you there. Oh, this is lame. So, well, it should reshade only that area. Unfortunately, it's not showing that. Hit graph. No, hit quit. Now hit graph. It's still there. All right, hit zoom standard. All right, zoom standard. Now we can do the integration all over again. And we were doing it between 1 and 3. And now it's showing, now we're only doing the lower area. All right, so did that match the answer you got?
It does.
Yeah, now I'm going to go to zoom standard again because I want to regraph it without the shaded area. And now how can you check the second part of your distance calculation?
Now we can check between 3 and 4. And that would be 1.5. And that comes out the same.
That's right. Good. That's actually quite useful because remember the first time I think you'd actually gotten an incorrect answer because of a calculator mistake, right? The first time when you were doing it on paper, you'd made a calculator mistake and we'd figured out the first one incorrectly. So it's good to see that we can still check our answers for that as well. And I think that's good practice anyway because it gives us more intuition to what we're actually doing here. All right, one thing this shows us is, one thing we haven't really been talking about is what the heck are definite integrals good for? We've been talking about how do you find areas? How do you find areas? But we haven't talked about why would you care what the area is. Well, now we can kind of see why. You would care what the area is under a velocity graph because the area under the velocity graph can be used to find displacement and distance. And those are interesting things. So that's a little hint at how these are used. Okay, so let me write this down. Okay, let's try this on your screen.
Real quick. So 12 minus 3x graph. Second calc. 3x 6 negative 4.5. Cool. Okay. Now for B. Preferred. The first part is defined when what time is velocity equal to 0. So we set velocity equal to 0. So okay. Now we have to start at 3, 4. Okay, so okay. So 12 times 4 minus 3 halves times 4 squared minus so bracket 12 times 4 minus 3 divided by 2 times 4 squared. I'm going to take this one step at a time. 24 minus 12 times 3 minus 3 divided by 2 times 3 squared. Okay, so we have 1.5 plus 4 plus 6, 7.5. Okay, I think, oh, that's weird. You got that. Okay, anyways. Alright, I'll check that. So, second calc. Let's see. From 3 to 4, we should get 1.5. We do. And then from 4 to 6, we should get 6. Oh, negative 6. And we do. So 7.5 feet. Okay, so here's our graph. And we started at 3. We started at 3. We ended at 6. So this is 3. It's 4, 5, 6. And I think that's all we need to show. I think that's good.
Okay, let's talk about that. So let's see. Why did the displacement come out negative?
That's because the area that's below the t-axis is larger than the area that's above.
That's right. So why didn't the distance come out negative?
Because distance is not a negative number or a negative concept.
Yeah, we use the absolute values. What is the area of the triangle above the axis?
1.5.
And what's the area of the triangle below the axis?
6.
You can see 1.5 minus 6 is negative 4.5. Okay. We should label the curve in your graph. What does that curve represent? That's important. Good. So again, we're learning here, why are areas interesting? Well, the area under a velocity graph tells you the distance or displacement. So that's interesting. Okay. Let's see. Looking at your move to the bottom right corner. I got confused there. I thought you were making a mistake there, but the calculator said you got it right. So let's see. Let me double check that. Oh, I guess I was the one who was confused. Okay. Go back up to the displacement calculation again. One second.
Okay.
Okay, so for the displacement, you calculated the antiderivative, right?
Right.
And then you plugged some numbers into the antiderivative. What's one of the numbers you plugged into the antiderivative?
I plugged in 6.
Yeah, and what did you get when you plugged in 6?
I got 18.
Now, if you go back to the bottom right corner, there was a place where you had to plug 6 into that antiderivative. Let's go back to that bottom right corner. What did you get when you plugged 6 into that antiderivative?
I got 18.
So my point is you could have avoided that calculation since you'd already plugged in the 6. It's not wrong, but it's like you already knew the earlier one was right because you checked it on your calculator. This just gives us another chance to make a mistake. I just wanted to point that out. Now go back up to the top left corner. Maybe you could zoom out so we can see them both at the same time. So what was the other number you plugged into the antiderivative up at for the displacement?
3.
And when you did that, what number came out?
22.5.
Right. Well, you also plugged 3 in the bottom right corner. And what did it come out to be?
22.5.
So,
I guess I only have to do one calculation.
Yeah. Now, there is one other thing. There was one new number that you plugged in there on the bottom. You didn't just plug in 6 and 3. There was one new time you had to plug in for the distance. What was the new time that they cared about besides t equals 3 and t equals 6?
When v equals 0, which is t equals 4.
That's right. So show where you did the t equals 4 calculation in the bottom right. Where did you plug in the 4, and what did you get?
24.
But if you think about it, you also had to do that on the right-hand side. You also used t equal 4 in the right-hand definite integral. And what did you get there?
24.
But you didn't have to do that calculation twice either, if you see what I'm saying. Now, it's not wrong, but it gives us more chances to make mistakes.
Yeah.
Well, I just wanted to point out you could reuse the numbers. I'm not, you do what's comfortable. So I wanted to point out every number here gets repeated. Every number here gets repeated. So if you see that, you could avoid some calculations if you feel comfortable with that. There's nothing wrong with the way you did it. I just wanted to point out that's a possibility. So you can reuse numbers if you want, or you can do it the way you did originally. Either of those is fine. The important thing is to check it on your calculator, because it's certainly easy to make calculator mistakes here. So it's definitely a good idea to check it on the calculator. All right, I'll go back to my screen. Okay, so again, the big lesson here is this is why definite integrals are useful. The definite integral of a velocity function is the area under the velocity function, and that turns out to tell you the distance or the displacement. That makes sense if the velocity is horizontal, but it actually works out even if the velocity is not horizontal. So we're about out of time, but why don't we squeeze in just one more? Let's squeeze in the web problem for this to make sure we have this down so we can do something new next time.
Okay.
So we'll do the web problem for this, and then we'll be able to go on to a new sub. We won't have to spend any more time on this next time. So let me write this down.
Is this a similar problem?
We'll see. One reason I want to do it is what I found in the past is often when I think problems are similar, when you actually do it, new issues come up. So I think it'll be similar, but we'll see as we go through it.
Okay.
The safest thing is always to do it. Okay, let's try this.
Okay.
Oh, there was one other thing I wanted to mention on that last problem. Do you still have the graph for the previous problem?
Yep.
On your calculator? What time did we find? What time did the object change direction at?
3.
Check your notes actually.
4.
Yeah, check that on your calculator. Can you see that on your calculator?
1, 2, 3, 4. Yeah.
So that's just a good thing to double check as well, to confirm that the calculator is confirming where it's crossing the axis. By the way, how could we see that this was going to be a downward sloping, the previous problem, how could we see it was a downward sloping line before you did the calculator?
Because the velocity function is 12 minus 3t and the slope is -3.
That's right. Of course, the calculator makes that easy, but even without the calculator, we should have been able to graph this function because we knew where it was crossing the axis and we knew the slope was negative. And then the calculator just confirmed that it was downward sloping and it crossed at 4. So those are good things to double check to make sure that we're understanding the problem. Okay, so now we can try this new problem.
Okay. So,
Make sure you'll have enough space.
I think I'll be
You
okay.
might. Okay, good.
Maybe not. Okay. So t squared minus 6t. And -8 plus 5, -3. Okay, and graph this. Y equals 2x minus 6. Graph. Should have a positive slope. Yep. And then second calc. 1 to 4. We get -3. Okay, that's -3 feet. I mean meters. Okay. Now for B. Okay, for B we do it like this. So start at 1. Oh wait, first we have to find t equals 0. So for part 1, 2t and v equals 0. 2t minus 6 equals 0. 2t equals 6. T equals 3. So part 2. We started at 1. Go to 3. And then let's see. 2t minus 6. And then value plus 3 to 4. Equals -6. T squared minus 6t and t squared minus 6t 3 to 4. Okay. So now we do. So let's see. What did we already do? We already did 1 to 4. I guess this doesn't really work. We plug in 4, we plug in 1. Okay. Alright, so 3 squared minus 6 times 3. Minus, well, we know 1 was -5. Absolute value of negative, well, four was -8. And 3 was, I haven't solved for yet. 3 squared minus 6 times 3. So 3 squared minus 6 times 3 is -9. -9 minus -5 is -4. So we're taking the absolute value of -4 plus the absolute value of -8 minus, I believe that was -4. Absolute value of -4. And this is equal to 8. So let's check. So second calc, lower limit 1, first limit 3, we should get 4. I mean -4. Yep. And then second calc, lower limit 3, upper limit 4. Wait. Wait, wrong function. No? Let's see. Yeah, I did something wrong. Okay, so this was -8 because we had already gotten that. That's right. And then this was 3 squared minus 6 times 3. It's -9. So this is -8 minus -9, which is 1. So this will be equal to 5. Okay, I think that's good. That's 5 meters. I need to draw a graph. Okay, so we cross the t-axis at 3. 1, 2, 3. And our slope is positive. And we started at 1. We ended at 4. Okay.
Okay, let's see. One thing that you did that was important is you noticed that the units had changed. Here we changed to meters. So it'd be a shame to lose credit for that. So it's good that you saw that and you did that correctly. Something else that what's the symbol that says when that marks the end of a definite integral?
D of t or
Yeah,
D
I
of
think we left that out in the first line for part B. I don't know whether the grader would be picky about that, but let's get that right on your notes. We haven't taken the antiderivative yet, so we have to include that still. Okay. All right. Something that looked like you were being careful about was when to take the absolute value. Notice when you're doing distance, should you automatically convert all the negatives into positives?
No.
No. You do get negative numbers as you're going along there. For example, you saw that when you plugged in 3, you got -9. Well, you didn't take the absolute value of that, so you have to make sure you're putting the absolute value signs in the exact right place and waiting until the right time to take the absolute values. And it looked like you were thinking about that and being careful about that, and that did come out correctly. It looks like we did make an arithmetic mistake at some point along the line, but you caught that on your calculator. One thing that might have helped is writing down more steps. So what did you get when you plugged in 3 into the antiderivative? You got -9, but you didn't write that down, and I think that might have led to the confusion there, especially if you're going to reuse your numbers. So you tried to use the reusing numbers technique, right? But if you're going to use the reusing numbers technique, you have to write down the numbers. Otherwise, it's easy to get confused there. But anyways, when the calculator didn't come out right, you were able to go back and see where you'd made the mistake there. Okay, well, I think this was the problem your instructor gave. This turned out to be a little easier than the ones I was giving you because the numbers didn't involve fractions. Okay, so I think this would be another good homework problem to do. Did you draw a graph?
I did not.
I think it would be better to draw the graph, though.
Okay.
Let's do that then.
1 to 3.
You know that it crosses at 2 because you figured out where v was 0. How do you know it's upward sloping?
Because the function is t minus 2, so the slope is 1.
Positive 1. Good.
Right.
Also, of course, you could then also confirm that on your, did you check your answers on your calculator?
Yep.
All right. So then you might have drawn a graph, and you could check on your graph that that graph looks correct. Okay.
Okay, so it crosses at 2. It goes from 1 to 3.
Okay, good. So looking at part A, you did the definite integral. Let's go back up or maybe zoom out. On part A, you did the definite integral from 1 to 3. That came out as 0. How you can explain with your graph why that came out as 0? What does that mean that it came out as 0?
It means that the area that's below the curve and the area the area that's below the x-axis and the area that's above the x-axis are the same.
That's right. Of course, you didn't quite draw it to scale, so they don't quite look exactly the same, but if we had drawn it to scale, those areas would be the same. So 0 feet looks like a correct answer for that. Good. And then down below, you did the integral from 1 to 2. What does that represent?
That represents this area that's below the x-axis.
Good. But then you took the absolute value to turn that into a positive number. And what does the integral from 2 to 3 represent?
The area that's above the x-axis.
Okay, good. Yeah, we should label those. And we should label what does the curve represent. What's the variable on the left-hand side of that equation?
Y. I should put,
yeah, v. What does v mean? What's v stand for?
V is velocity.
That's right. So which way was the object moving before time 2?
It was moving downwards.
Because the velocity was negative. Then it shifted direction and moved upwards. Okay, so I think drawing that graph would be a good addition to these problems. I think they might be looking for that here. You got 1 foot as your answer. You gave the units for that, feet and feet. Okay, so we put some time into practicing those problems, and I think we got that right. You should stop to say, this is what calculus is good for, this is what integration is good for. Notice that what you knew here was the object's velocity. But from that velocity, by the magic of integration, you were able to figure out its distance and displacement. So this is actually the only application you're learn in your course for integration. There's many more, but this gives us one little hint of how integration can be useful in this case. Okay, excellent. All right, so that's good progress on that. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.